Episode 92, Talking Cosmology with Phil Halper. This is Matthew, and this episode is a replay of a conversation we had in 2020 with Phil Halper. It was originally broadcast on our Proscenium podcast, but since all of our effort now goes into Still Unbelievable, and this is a discussion that has been referenced on a few occasions, it seemed appropriate to republish it on Still Unbelievable. As always, see the show notes for links to additional resources mentioned in the show. Hello everybody and welcome to another episode. My regular host next to me here, Andrew. Hello from across the pond.
Hello.
And we have a very special guest here, somebody who helped us with writing of the Still Unbelievable book, wrote 2 chapters for it, I believe, and has been on the Unbelievable podcast a number of times, 4 or was it 5, I think, at the last count. Anyway, welcome on to Proscenium, Phil. It's wonderful to talk to you.
Well, thank you very much for having me.
Yeah, it's great to have you. It is long overdue, I must admit, but you are a YouTuber. You are a very popular YouTuber, actually, and I do highly recommend your YouTube channel. You talk to some of the world's leading cosmologists, including Stephen Hawking, Sir Roger Penrose, Alan Guth, and there are many, many others. You've got a series called Before the Big Bang, which has attracted millions of views and lots of very good reviews. And you've been appointed journalist in resident at the Penn State Institute for Gravitation and the Cosmos, and you're a fellow of the Royal Astronomical Society. We wanted to have you on to talk about cosmology, the beginning of the universe. Let's just start with a very simple question. Did the universe begin?
Well, that is a very good question. And the short answer is nobody knows. It was widely believed that the universe did have a beginning. And I think that was widely believed up till probably maybe late 90s, early 21st century. But now I think most cosmologists would be more open-minded that maybe the universe didn't have a beginning. But the short answer is we don't know.
So why did cosmologists, up until the last couple of decades, think that we did have a beginning?
Right.
Give us some of that history.
Okay. So what happened was, let's go back to 1915. Albert Einstein came up with his general theory of relativity that describes space-time as this dynamical entity. So it was soon realized that if it's a dynamical entity, it can stretch and it can compress. So it was people like Alexander Friedman and Georges Lemaitre in the 1920s. They found that there were solutions to Einstein's equations that basically were saying, well, the universe should really either be expanding or contracting. It was then observed that it's expanding. So if it's expanding, then we can trace that expansion backwards in time. So it's getting more and more compressed, it's contracting, and you get to a point where there's no distance between any sort of points in space. So then the density, the pressure, the temperature, the curvature of the universe all become infinity. So you can't extrapolate backwards anymore. So that's what's called a singularity. And so therefore it's inferred that that's the beginning of the universe. But back in the 20s, it wasn't really taken very seriously. And even going into up to the 1960s, these singularity theorems were known to have a lot of unreasonable assumptions. I should probably say the most particular unreasonable assumption that was highlighted at the time was that the universe had to be perfectly symmetrical. And that's just obviously not true. I mean, there are some regions that are more dense than others. We have galaxies and all kinds of structures. So people thought, well, this singularity is just a sort of artifact of having this unrealistic assumption. So it wasn't, I don't think it was taken that seriously. And then in the 1960s, you had 2 things happen. One was we got a lot more experimental evidence to confirm that there was a Big Bang. And we'll go into a little later what we mean by the phrase Big Bang, but let's put that aside for the moment. The other thing that was discovered was by Penrose and Hawking. And they showed that the singularity theorems were much more robust than people thought. That you could relax some of these unrealistic assumptions and you're still going to get a singularity. So therefore, people thought, well, therefore, there really is a singularity. There was a singular, they call it a singular beginning to the universe. And that was the view probably up until, well, I'm not quite sure exactly when, but let's say, late 20th century.
And so at some point in the late 20th century, I know at least one new idea was forwarded, I think, in 1999 that we'll get into. Loop quantum cosmology, I think, first made a splash in the late 90s, 98 or 99 maybe. But
I think it's probably early 2000s, actually. Early 2000s.
Was it? Okay.
Yeah.
But at some point, this idea changed, right? The idea that we had this sort of fixed beginning from this singularity, that idea started to change.
That's right.
So what caused that shift in thinking?
Okay, I would say there's a few things. Off the top of my head, I'm going to go pick top three. So the first one was that in the sort of late 70s, early 80s, people began to believe that there was a period of very rapid expansion called inflation. And we should go into inflation in a bit of depth. But for the moment, let's just hold that for a moment and just say there was this period of very rapid expansion that was believed to take place in the early universe. And that period of rapid expansion is associated with gravity being repulsive rather than attractive. So normally we think of gravity as an attractive force. If I jump up, I'm going to come back down to the Earth. I'm not going to fly off into space just by jumping up and down. And that was one of the assumptions of the Penrose-Hawking theorem, because even though it had relaxed a lot of assumptions, it had said, no, that assumption doesn't matter. You're still going to get a singularity. There still are assumptions in these theorems. So, sure. And one of them was that gravity is always attractive. So when inflation came out, it was realized, oh, hang on, gravity is not always attractive. So that cast the first level of doubt, shall we say. Then in 1998, it was discovered that the universe is accelerating in its expansion. So the rate of expansion of the universe is not slowing down, as a lot of people thought, but is actually speeding up. And again, that is modeled as there being some repulsive gravitational force. So now we have sort of direct experimental evidence that there is repulsive gravity. So this repulsive gravity violates these singularity theorems. So that's reason number one. I should say inflation is reason number one. Dark energy is reason number two. And then the third one is that another assumption of these Penrose-Hawking theorems is that we describe gravity using this theory that Einstein came up with in 1915 called general relativity. And general relativity is a beautiful theory. It's incredibly well tested, but it is in conflict with another theory that's incredibly well tested, which is called quantum mechanics. And quantum mechanics, so if you think of general relativity as our theory of gravity, quantum mechanics sort of governs other forces of nature, but it's particularly relevant for very small things like subatomic particles. And general relativity you can think of as being very relevant for very big things like large clusters of galaxies and the large scale structure of the universe. So general relativity and quantum mechanics are in conflict. And people have been in fact, Einstein mentioned this even a year after publishing general relativity. He said, general relativity is going to have to be modified to take quantum mechanics into account. And that has been a long struggle to get theories of let's say, quantum gravity. In the 1980s, that started to change. Physicists developed some, let's say, not confirmed theories of quantum gravity, but at least theories that seemed plausible and seemed like they had a lot going for them. So the two in particular were string theory and loop quantum gravity. They're two most popular, shall we say, but there are others. And so people started to think, well, hang on, we're not using these and we need to. So maybe we shouldn't believe these singularity theorems, and probably these singularities are going to be resolved when we use these theorems.
In your view right now, where are we in terms of a resolution?
None of these theories of quantum gravity have been experimentally tested. So it's still up in the air. But I think everyone agrees, well, not everyone, probably most people agree that we will need a quantum theory of gravity to resolve this question. Without that, we just can't confidently say anything about what really happened at the Big Bang. Although it does depend on what you mean by Big Bang, and we should come back to that issue. However, having said that, some of these, so there's been a lot of work on trying to develop testable models of cosmology, of the Big Bang, using things like string theory, using things like loop quantum gravity, and Hojava gravity is another competitor. And there's been some progress where we could actually point to, a definite concrete models. They look plausible, shall we say, and they even make kind of tentative predictions. There's a bit of ambiguity about the predictions, but they're definitely looking more robust and maybe testable in the future.
When you think of loop quantum cosmology and dark energy and what's happening right now, you're certainly better read and better connected with these things than I am. So tell me what your thought was there in regard to LQC and dark energy.
Well, probably we should explain what LQC is.
Sure.
First off, of course, people should watch our videos about it. So if you go on our channel, type in loop quantum cosmology, and then my channel name is skydivephil, all one word, like jumping out of a plane, Phil.
Right. And that's YouTube, boys and girls.
Yeah, onto YouTube. And then they can go into more detail about it. But just to give you the short summary, so recall that I said loop quantum gravity is a potential candidate for giving us a quantum theory of gravity. And that's needed because quantum mechanics, our theory, they're very small, general relativity, our theory, they're very big, are in conflict with each other. And we should say, for the most part, that conflict doesn't really matter. If you're a particle physicist, you don't really need gravity. You don't need general relativity. And if you're a cosmologist, you don't really care about quantum mechanics, if you're looking at the evolution of the whole universe. However, if we believe that the entire observable universe was squeezed into space, far smaller than an atom, but then you are going to need quantum gravity. And that's kind of the whole point of this whole story, really, that these notions that the universe began with a Big Bang singularity don't include quantum effects. So that's why we can't trust it. So loop quantum gravity is one attempt to write a general quantum theory of relativity. And loop quantum cosmology is the attempt to apply those principles to cosmology. And what loop quantum cosmology seems to be telling us is that the Big Bang singularity is replaced by a big bounce. So the universe before the Big Bang was contracting, and then it's expanding. And the reason for that, basically, is that in loop quantum gravity, space is made out of sort of space-time atoms. And so space-time is discrete, which means that you can't keep cutting it up into smaller and smaller pieces. So you might have heard of the phrase space-time continuum. Have you heard of that? Right. Yep. So a continuum is something that you can just cut up indefinitely. You can just keep making it smaller and smaller pieces, and you can just go on forever. And loop quantum gravity says no, you can't do that. So that means that space-time, there's a limited amount of stuff you can squeeze into a certain space. Whereas relativity sort of saying there isn't. You can just squeeze in indefinite amounts of stuff. And so basically space-time can get sort of full up. And if it gets full up, then if you try and squeeze more things into it, those things will just bounce off. I mean, imagine dropping socks into a laundry basket where you keep dropping your socks, but eventually that laundry basket's full up. And if you drop more socks into it, they'll just pile up and come out, Right. So space is like that in loop quantum gravity. So basically, instead of getting a singularity, you get to a sort of full up state of space, and then gravity switches and it becomes this repulsive force, a bit like inflation, and so you get a bounce rather than a bang. So that's basically the mainstream view of loop quantum cosmology researchers. So that's what LQC says. Now, dark energy is the name given to what we think is driving the universe to accelerate. Remember, we said the universe is accelerating in its expansion. And what's causing that is unknown. So one very recent idea that's come up in loop quantum gravity is that these atoms of space-time, the way they behave, actually generate this dark energy. So it's a sort of friction with the atoms of space. And so that's a very new idea. We've made some recent films reporting on the last Loop Quantum Gravity conference, and that was in our second film on that topic. But that is very new. I'm not even sure that the rest of the Loop Quantum Gravity community accepts that. Maybe they do. I'm not sure yet. And then even if they do, of course, we still don't know if Loop Quantum Gravity is the right theory of quantum gravity. We should probably mention there are others, like string theory and Hodge-Valicious gravity and causal set theory. So these are still open questions.
But I'm curious because you mentioned the most recent LQC conference. Is there some proposed experimental mechanism by which we could test a portion of space, right? To test some part of the universe to see whether this expansion is indeed due to the things that you've suggested. Is there an experimental mechanism, or at this point
they're looking into that? There are potential experimental checks on this. At the moment, the signal that they would produce is too small for any experiment to notice. But they're investigating. This is very, very new.
Yeah.
So we shall see, but it's certainly being investigated. But I think, moreover, that I wouldn't focus too much on this issue of can loop quantum gravity explain dark energy. I think the thing that's probably more relevant to this question of the bigger question of, did the universe have a beginning, or what was before the Big Bang, and so on, is, could we test any of these models? And there are proposals, that people are making for experimental tests of whether there was a big bounce, and whether it's the big bounce that loop quantum cosmology predicts, because this idea of a bouncing universe is not specific to that particular theory of quantum gravity. There are other proposals that also give you a bounce. And so people are now working on, well, how do we test this? And the most promising candidate is to look at the oldest light in the universe, which is a cosmic microwave background. Now, this light was not emitted at the Big Bang. It was emitted about 400,000 years after the Big Bang. And it has, it's pretty uniform, and hopefully we'll get to talk about inflationary cosmology as well, but which explains that, well, tries to explain that uniformity. And but if we look very closely at this microwave light, we find that about 1 part, so up to about 1 part in 100,000, it's the same temperature everywhere in the sky. But once you go past 1 part in 100,000, you start to see tiny temperature differences. And then what cosmologists want to do is to look at the statistics of these temperature differences, because this is, maybe a way to find out what's behind the curtain, as it were, what happened before the cosmic microwave background was emitted, because what happened before will determine the statistics of these sort of hot spots and cold spots. So people have created models using these different theories and made predictions for the cosmic microwave background. And some of them have claimed some successes, but it's still a bit early days. It's still a bit of a rough work in progress at the moment before we can really say anything definitive. But there certainly are sort of claims out there that, there are certain features in the cosmic microwave background that can be explained using like a bouncing cosmology. Unfortunately, at the moment, the features in the cosmic microwave background, they're probably not statistically significant enough for us to say that's a real feature, So it's still a work in progress, and certainly nothing definitive has been found, but people are working on it, and there are some, let's say, exciting leads.
Well, and talk for a second, if you can, because you're plugged into that community about how we measure tiny differences in the CMB, the cosmic microwave background, to levels like 1 part in 1,000 or even finer at distances more than just right around us. How, so that's got to be a huge instrumental challenge, right?
It is difficult. So basically, they use these things called bolometers, which are sort of things that are very sensitive to microwaves. So they can detect, tiny temperature variations. Now, but we can only detect them here where we are. We can't go to another galaxy and see what they're seeing. So that's all we can do. But what we can do is look at different directions in the sky, and what we find is that it's extremely uniform. But these bolometers, these microwave receivers, they are very, very sensitive now. So that's a lot of the experimental design. And you have to keep, one of the things is, so like the last satellite that went up to do this was called the Planck satellite. And, that had extremely high resolution, but it had to be flown well away from the Earth. So it's not in orbit around the Earth. It's actually sent to this point in space called L2, which is, I don't know how.
Lagrange 2. Yeah.
That's right, yeah. So I don't know how far that is from Earth, but it's far, it's further than the moon for sure. They have to be cooled cryogenically, so the spacecraft can only run for so many years because eventually it runs out of coolant. So that's another thing, you have to keep the spacecraft colder than the temperature that you're looking at. And the temperature you're looking at is like 2.7 Kelvin. It was the rough temperature of the microwave background. So there are a lot
if your equipment gets too hot, you can no longer measure.
Correct. So there's a lot of engineering challenges that go into these, and that interesting thing is, when you send something into space, you have to spend years testing it and making sure that it can survive the harsh conditions of space. And once it's out there, of course, it can't be repaired or changed. So people have got better instruments on the ground, and there are also now a lot of interesting ground observatories going up. So they can get better equipment, but of course it's better to be in space. So there's trade-offs that you have to make when you're making these experimental designs.
Right. So just to recap that just for a moment, the way that we're testing beyond what appears to be a very heterogeneous environment, the cosmic microwave background being a consistent temperature, is, yes, we're stuck here doing that work, but we look in various directions in the sky and we're observing that the CMB is not quite as, sorry, I said heterogeneous. It's not quite as homogeneous as we thought. Beyond 1 part in 1,000 or whatever it is, there's some, it's heterogeneous and it is different depending on where we aim our instruments.
Well, it is pretty uniform across the whole sky. It's only 1 part. Once you get to 1 part in 100,000, you start to see differences. And I think cosmologists always knew that there would be these differences, because if there wasn't, if the CMB was perfectly uniform, then no galaxies would form. It's got to be some differences in the early universe so that there can be differences in the late universe. The question is, the detail, the fine detail of the statistics of the cosmic microwave background. But yeah, we are trapped on the Earth. And so there is always a problem which there's no getting out of, really, which is, well, maybe we can only see so much of the universe. And we're just stuck with that. And we have to try and make models that can account for that. And there's always a possibility when you look at the universe where you've only got one universe that you can look at. You can't look at another universe and compare it. So that's a limit on our knowledge, basically, and we're just stuck with that. But that doesn't mean that we can't try and test some of these exciting ideas of, what might have happened before the Big Bang and so on.
Now that brings us back to a place where you put a pin in the map a few minutes ago, which was, what can it mean to be before the Big Bang?
Right.
What models lead us to think that there was something sort of before a Big Bang, and that's going to get us into expansion, right?
Yeah, well, right, indeed. So let's start with inflationary cosmology. So this was an idea that was proposed at the end of 1979. And there are a lot of problems with the standard Big Bang model. That doesn't mean the Big Bang model is wrong, because we have overwhelming evidence there was some type of Big Bang event, but we don't know the precise nature of it. What we can say is that the universe is expanding in the sense of distant galaxies are moving away from us, or moving away from each other, I should say. And so space is stretching, and if we go back in time, that means it's contracting, it's getting hotter and denser. And but there are sort of some problems with the standard Big Bang model. And I won't, if you want to know what they are in detail, you should watch our film on inflationary cosmology, which is called Eternal Inflation and the Multiverse, or Before the Big Bang 4, Eternal Inflation and the Multiverse. And we interviewed the author of Inflationary Cosmology, Alan Guth, and some other of his colleagues. And so what inflation is this very rapid expansion, and this fixes a lot of these technical problems that existed for the standard Big Bang model. So it's sort of, there were these four famous problems, and inflation comes along and says there was this incredibly rapid expansion, and that turns out fixes all of these problems at once. So cosmologists were amazed by this theory, and it caught on very, very rapidly, and is now the dominant theory of how galaxies formed. Basically, what were the original seeds of galaxies, and this rapid expansion is really rapid. So we're talking about the universe doubling in size in the inflationary epoch every 10 trillionth of a trillionth of a trillionth of a second. So that's pretty damn fast.
That's pretty fast.
Yeah.
Now, but when you say that, so when we're talking about a universe doubling every trillionth of a trillionth of a trillionth of a second, if I repeated you right, apologies if I didn't. When we talk about that sort of expansion, one of the things that would seem to be the case is that we're also talking about an incredibly small universe at that point.
Well, we have to be careful. It's the observable universe, because we don't know whether the whole universe could be infinite in size,
sure.
and which means it could have been infinite in size even at the Big Bang.
Okay, now we're coming back to that.
Right, right. Well, it's a misconception to think that the universe was small at the Big Bang. What is correct to say is that our observable patch of the universe was small at the Big Bang. So
sure.
all the universe that we can see was smaller. But if the universe is infinite in size now, then it was infinite in size then. But what you have to remember that what the Big Bang is saying is that the density of the universe is changing. It's not really the size of the universe that's changing. Or there might be, if the universe is finite in size, which it might be, then sure, the universe is growing in size. But we don't know whether the universe is finite in size. It might be infinite, it might be finite. We just don't know. So if it's finite, then sure, it's growing in size. But if it's infinite, then what does it mean to say it's growing in size? You know,
right? Of course, so
what we can say is that the density of the universe is changing, which means any particular patch of the universe is growing in size. So we can say that our observable patch was very small at the Big Bang, and the whole point of inflation was that it was much smaller than it would have been had there not been any inflation. That is actually what solves a lot of cosmological problems, because if you look at some of the details of Big Bang cosmology, you get a lot of puzzles, because it turns out the universe wasn't small enough, and what inflation does for you is make it much smaller.
So forgive me if I say this back to you wrong. I'm not sure that I grasp it, but I'm going to try. So every trillionth of a trillionth of a trillionth of a second, if the universe was just being true to the terminology we use, doubling in size, if it was really more about density, what we're talking about is the universe having in density.
So the
observable universe.
The observable universe is growing in size. So the patch of the universe that we can see, think of it this way. If you look out the window, you can only see so much of the Earth, right? You can't see the whole planet. You can only see a bit of the planet, right? So think
Maybe
of
you guys can't. No, that's right. We can only see a very small bit of the planet.
right. You can
Sure.
only see to your horizon, right? So it's the
Right.
same with the universe. You can only see to your horizon, right? So
Right.
there's a patch of the universe that we can call our observable universe, but there's no reason to think that the universe just stops there, right? There's
Sure.
similar. You wouldn't think that the Earth just stops at where you see the horizon, right?
Right. In
So
fact, that's the horizon problem, if I understand it correctly.
the horizon problem is related to that, and we can go into
Yeah.
it if you want, but probably better to just watch our videos and we explain that. But so
Okay.
the issue is, so therefore the observable universe is growing in size at this rapid rate, okay? And therefore, of course, the density of the universe is well, actually in inflation, I shouldn't say that because the universe is just made out of inflationary energy at this point. So the density is not,
Mm,
it's only later on when there's matter and radiation that the density declines.
okay. So I'm not sure how to grapple with that. Just it's sort of inflationary energy and no mass. So at what time scale are we here? Is this before or after the
So
Big
this is
Bang?
an excellent question. It depends how we define the phrase Big Bang, and this will hopefully clear up a lot of the confusion. So
Mm,
there are at least two ways to define the phrase Big Bang. One is to say it's an evolution from a singularity, where the space-time, curvature, density, pressure, and so on are all infinite. Now, very few people take that seriously anymore. Most people don't think there was a singularity. So instead, there's another way to define Big Bang, which is perfectly consistent with all the observational evidence that we have that the universe is expanding and so on, but doesn't worry about this issue of whether there was a singularity. And that is to define the universe as evolving from a super hot, dense state. So that is what all the observational evidence points to, that there was this hot, dense state. And so we could distinguish, if you like, between the Big Bang singularity and the Big Bang expansion. So think of
mm,
that's its distinction. So if we
mhm,
think of the Big Bang expansion, inflation happens before the Big Bang. Why? Because during the inflationary era, the universe is extremely cold. So what happens is when inflation ends, the energy in the inflating space is sort of dumped into matter and radiation, and all the matter and radiation that we see around us comes from the decaying of this inflating space. So when inflation ends, that is the Big Bang.
mhm.
So in that sense, then inflation is a prequel. In fact, Alan Guth, the inventor of inflation, calls it a prequel to the hot Big Bang. So inflation happens before the Big Bang. However, if you believed that there was a singularity, then inflation is after the Big Bang. But since no one really takes a singularity very seriously, I think it's better to say that inflation happened before the Big Bang. And we should say that inflation is mainstream cosmology. Most observational cosmologists will say there's evidence for inflation. Now, having said that, there are some alternative theories to inflation, and we shouldn't discount them. I think inflation, I would describe it as, if you like, the leading horse in the race, but it's not quite crossed the finish line yet. So it's still somewhat controversial, even though I think the majority of cosmologists will buy into inflation. But if inflation happened, then inflation is what happened before the Big Bang.
And that's the sort of statement that I think hasn't made its way out into sort of popular understanding. Right?
Yes, I agree. I agree. And in fact, some textbooks will say, oh, inflation happened just after the Big Bang, a tiny fraction of a second. And that's because when inflation was first invented, Alan Guth gave a talk. It was the very first talk on inflation. And he called, the name of the talk was 10 to the minus 35 seconds after the Big Bang. But, once the theory was developed more, then people realized, wait a minute, if this is true, then inflation has to happen before the Big Bang. And in fact, Alan Guth himself now, as I say, describes it as a prequel. But that just wasn't appreciated initially. So this, was realized later, but it was sort of too late. People, the idea just got ingrained. And in fact, I did a course in astronomy and they teach you, inflation is what happened after the Big Bang. But it's really, I don't think, correct.
So that's it. I think that's the sort of thing that has a lot of momentum behind it that will be hard to change for two reasons, right? One is it's very easy to understand, right? It's easy to think, well, Big Bang, and then there was some inflation, right? And when we were talking about it a moment ago, it took me a minute or two to get my head around the idea that there could be an inflation prior to the Big Bang, right? Where does matter fit into this picture? Well, if there is energy that's dumped into the Big Bang, and that's sort of, this, or there's our matter and the universe that we sort of experience comes after that inflation. Well, I can make sense of that, but that takes a minute or two.
Oh yeah, it's not easy.
No, and I think right now may be the first moment that I've come across inflation happening prior to the Big Bang.
Right? Well, you should watch our video because we talk about that.
Yeah, well, and everyone should go and just sort of start at the beginning. You've got.
In fact, there's another video that we made that's shorter. There's the video that we made with Alan Guth and his colleagues is called Before the Big Bang 4, Eternal Inflation in the Multiverse. But there was another video, and that's about an hour long, I think. I don't know exactly how long it is, but it's somewhere between 45 minutes and an hour, something like that. But there's another video that we made that was much shorter, and that is called The Big Bang's New Meaning. And this is what we're trying to unpack. And you'll hear people like Stephen Hawking and Alan Guth and Roger Penrose all basically trying to reinforce this point, that really the Big Bang has changed its meaning. So back in the 20th century, the phrase Big Bang was very much associated with an absolute beginning of time, with a singularity. But I think now in the 21st century, the Big Bang has kind of changed its meaning, and it really now refers to this just hot, dense state. So, and that it really is because that is what the evidence is telling us. All the evidence that you hear about, the redshift of the galaxies and the cosmic microwave background and all these things that are supposedly evidence of the Big Bang. Yes, they're evidence of the Big Bang expansion, but they are not evidence of a Big Bang singularity, because a singularity does not make predictions for what we should observe. So there's no evidence for a Big Bang singularity other than theory. But since we've discussed, there are reasons to not take that theory seriously as describing our universe.
So with this rethinking of the beginning of the universe and everything we know starting from the singularity, which you've quite well explained is just dropping out of favor, but usually we think of time being associated with starting at that point as well. So how does the bounce affect our ideas of time and how we measure time up to and beyond the beginning of the universe?
So there are different bouncing models. Now we're going away from the idea of inflation, because inflation and bouncing cosmologies are different ideas, although they can be connected together. You could have a bounce and then inflation, or you could have a bounce without inflation. And there are some cosmologists like Paul Steinhardt and Robert Brandenberger who have developed models of bouncing universes where actually the conditions in the pre-bounce phase sort of replace inflation. So maybe you don't need inflation, and maybe inflation didn't happen. So we should distinguish between some different bouncing models. So one is that inflation is replaced by a bounce, but others are there's a bounce and inflation. Then there's another distinction to be made, where at the bounce there's something called the arrow of time, and that in some models reverses at the bounce, and in some models it doesn't. So we should unpack what that means for listeners. Mm-hmm. So if we think of it this way, if you think of a clock, so imagine you watch a video of a clock. Now you can tell whether that video is playing forwards or backwards, right? It's pretty easy, right? Mm-hmm. If it's going clockwise, it's being forward in time. If it's going anti-clockwise, it's going backwards in time, right? But now think of another type of clock. Look at a pendulum. Now, if you watch a video of a pendulum, you cannot tell whether it's forwards or backwards in time, right?
Right.
So this distinction then is called the arrow of time. Now, the weird thing is that the fundamental laws of physics don't seem to have an arrow of time, but yet we certainly experience one. So the question is, how does the arrow of time arise and what causes it? Now, in some models of the bouncing universe, the arrow of time if you think of our branch of the universe, the expanding branch, our arrow of time is moving forwards, okay? If we were to look backwards at the previous universe, we would see the arrow pointing not in our direction, but away from us. So if you like, the people in the other branch of the universe, they think that we're in their past and we think they are in our past. Because this arrow of time, if you think of an arrow, is pointing in opposite directions. So they see themselves going forwards in time, but we see them going back. So one idea is that, and this is called the Janus universe, named after a Roman god who had two faces pointing in the opposite direction, looking into the future and looking into the past. So these are known as Janus models, and they have this reversal of the arrow of time. But other bouncing models do not have that. The time just marches on, and the fact that there's a bounce doesn't sort of matter. And so there are different models of the bounce, and some, if you like, have this reversal of the arrow of time, and some don't.
So I can see it makes sense to me in a universe where there might be a bounce, that the arrow of time is irrelevant because the universe is just repeating a cycle, right? And so we might arbitrarily measure time from the beginning that we see, but that wouldn't mean that was the beginning in some objective sense.
Well, we have to be a little careful. So if there's a bouncing universe, it does not follow that there's a cyclic universe. So that's a big misunderstanding. And we should probably clear that up. So if we think of the universe as you see it described in your textbooks with standard Big Bang model, it kind of looks like a big ice cream cone. And so the idea that people have, if there's a bouncing universe, imagine you've got now two ice cream cones and you sort of squeeze them together. And then you have a series of these and it's sort of continually cycling. So you expands and then contracts, expands and contracts. And this just keeps going on forever. That's a cyclic universe. And there are models that people are investigating today and promoting today that are cyclic, just like that. However, that if there was a bounce, and various models of quantum gravity, I think, seem to be hinting at that, then it doesn't follow that it is cyclic, because it could just be that it's what we call a one-shot bounce, if you like. So there was a contracting universe, and then there's an expanding universe on the other side. So now think of not an ice cream cone, but instead think of an hourglass. So there's no repetitive behavior. It's just a contracting universe just stuck with an expanding universe sort of next to it, as it were. They're joined with what's called a quantum bridge in the middle. So that is a possibility. And observational evidence sort of seems to hint probably more in favor of that rather than a cyclic universe. However, it's certainly not a clear enough picture to rule out a cyclic universe. There are a number of cyclic models that are sort of still on the market today that I think should be taken seriously, and they might turn out to be right. But the point I want to make is that if there was a bounce, it doesn't follow that there's a cycle. That may or may not be true.
Sure. And that,
maybe we should say this: a cyclic model generally has a bounce, but a bouncing model does not necessarily cycle. Although I should say, even with that caveat, there are models of cyclic universe that don't actually have a bounce at all. Roger Penrose has a model called conformal cyclic cosmology, which actually the universe never contracts. It's always expanding. And again, we made a film, in fact we made two films with Roger Penrose about his model. And if people want to find out more about that, they can watch our films. But the bottom line is, there is even cyclic models, are even cyclic models that don't even have a bounce.
I wonder if you can, when we think about an hourglass universe. So there was a period of contraction into this sort of quantum bridge. And we are now on the other side of that bridge, and apparently in a state of continuous expansion.
Yes.
The obvious question that sort of comes to mind is, on the other side of the quantum bridge, where the ice cream cone, if you will, is at its largest point, right? What got that ball rolling, right? Where does all of that come from? Because we're used to thinking of.
Yeah.
Go ahead.
I don't think science is in any position to really go there at the moment. I mean,
we want you on record. This is your perfect chance.
Okay. Well, all right. It depends. I mean, obviously there are different models.
Sure.
If for those models that are cyclic, it's always been that way, I guess you could say. So it never began. So that's one possibility. Another possibility is that it did begin and then it started to cycle. So that's another possibility. For those models, there's for those models that think, if it's like a mirror image, then the universe would have started out maybe infinitely big and empty, and then contracted and started to get more dense and so on. But I mean, I think what scientists really are trying to do, we can analyze the evolution of the universe with a very high level of confidence going a certain time back in time. So roughly 14 billion years. Yeah.
Right.
And then as we get into, I think the first sort of more controversial bit is where we get into the inflationary epoch. That's somewhat controversial whether inflation happened. I think most cosmologists think it did, but not everyone. There's some serious cosmologists who've got alternatives. So that's the first bit of sort of controversy. And then assuming inflation did happen, we can still ask the question, well, what happened before inflation? Maybe there was a balance. And what cosmologists are trying to do is trying to push the envelope. Can they get to a point, 15 billion years, ago, where the universe maybe was contracting or maybe it was doing something else? I think, to ask what was happening infinitely long ago is probably asking a bit too much. There are models, I should say, though, that do have a definite beginning. And we can talk about those if you like. And they describe the very ultimate origin of the universe. And so, that's another option on the table.
I wanted to ask about what it means for proposals for the heat death of our universe, but I feel that might be taking us too far away from talking about did our universe have a beginning. But it's kind of piqued my interest. So if it only takes a couple of seconds to answer that one, I'd be interested in that question.
So sure. Okay. So is there going to be a heat death? Is that the question? And then what happens after that?
Yes.
Okay.
I mean, because do any of these models affect that?
Generally, I mean, some of them do. Like the Penrose's model is a cyclic universe model, and to have a heat death, we have to assume that the dark energy, whatever the thing that is causing the universe to accelerate in its expansion, is a constant. It's not changing its value over time. So assuming that's true, then we do have a heat death for the universe. So what we mean by heat death, it's really the death of heat. It's not a death by heat. It's like the death of heat. The universe just gets colder and colder and colder. So that is probably where most cosmologists would put their money at the moment, because we haven't seen any evidence that dark energy, or any convincing evidence, is changing over time. There have been some hints that might be true, but we're building better, telescopes to try and check that. But so at the moment, I think the consensus would be that dark energy is a constant, but it might not be, or we definitely have to keep an open mind that it might not be. So assuming that it is, then we do have this death of heat. And the universe just becomes a cold, empty place with nothing in it. Now, there have been models like Penrose's model, and there's another one called the Baum-Frampton model, which actually cycle, from this empty state, as it were. So in Penrose's model, his idea is that when you get to this far future where there's nothing in the universe, then the universe loses track of its scale, because you need mass in the universe. You need to have matter to build clocks and rulers. And if you don't have that, then there's no notion of time or even scale. And so a universe that's just energy with no scale, if you like, is kind of the same as the Big Bang. So what he says is that it goes through this transformation, and it's a bit weird to think about. But so that's why you need to watch the film for the more detailed explanation.
Clearly.
But this is called conformal cyclic cosmology. And if you go on our YouTube channel, the skydivephil YouTube channel, and you find we've actually made 2 films with Roger about this model. And so that actually, so there's a possibility that the universe sort of starts again in this cold, empty state. But of course, it depends on whether you buy into Roger's model, and he has some assumptions that you've got to make, which are somewhat speculative. But he argues that there's a big advantage to this model, because what he claims is that the entropy effectively gets reset, and that would explain why we have this very low entropy start to the Big Bang, and which inflation doesn't really address, and a lot of models don't address. And he's sort of saying that my model does address this biggest of problems. Why was the entropy so low at the Big Bang? It seems to be extraordinarily low. So why? Something must have put it there. So, and his argument, and there's another model actually called the Bound-Frampton model, which, although it's different to Roger's model, is kind of making the same sort of argument that, you know, in the far future of the universe, you get to this point where the entropy can actually get reset. But they've got certain assumptions that they need to make this argument. But you know, those are some possibilities. Of course, another possibility is that the universe just nothing happens. You know, it's just dead, cold, boring place, and that's the end of it. You know.
So that sort of brings us full circle, doesn't it? Because Matthew started us off with the question: did the universe have a beginning? And we're now down to: does the universe have an end? And I wonder, from your perspective, what you think most cosmologists' views are now. So we've sort of turned away from a Big Bang and from singularities, and we have some understanding of a beginning. What do you think the common understanding of end is? Is it heat death? And, you know, that's the
well, I can interrupt because our videos haven't really touched on the end of the universe. They really start with the beginning of the universe. And if there's a cyclic model, then they're the same. You know, the beginning and the end are the same. But of course, we don't know if any of these cyclic models are correct. They may or may not be, and that's being investigated at the moment. So I would say the consensus view is probably dark energy is a constant, so we get this heat death. But it's definitely, I think most people are pretty open-minded about it because we know very little about dark energy. And so to really put your neck out and say it's a constant, therefore we have a heat death, that's probably premature. So I think, you know, it's an open question, just like the beginning is an open question.
Right. Yeah. And it's the beginning is where all the sexy stuff is happening. Anyway, going back to the beginning and your suggestion that the arrow of time might move in the opposite direction away from the bounce, which just messes with my head really, and it's giving me flashbacks to a film that I watched in cinema with my daughter last week, Tenet, which is currently at cinemas, which is a similar sort of thing. But the question I really want to ask though about this time and the two universes, the past and the future, or us and them, going in opposite directions and both forwards away from the center. Could that explain ideas of the multiverse? And could that be considered the same as the multiverse, or is it different to the multiverse?
I think it's different. I think generally when people, obviously how you define multiverse, you know, is up for grabs. But I think generally the way people think about the multiverse is really a different topic, but it's worth exploring, because what people don't realize is how, I want to say, implicitly mainstream the multiverse is. And I say implicit because a lot of people don't realize this. But remember that we said there's believed to be this inflation epoch. And that is pretty mainstream cosmology. Although, as I said, not everyone accepts it and there are alternatives. But But it turns out that inflation seems to predict that we live in a multiverse. And so probably it would be worth exploring why that is and how that is. Shall we do that?
Yeah, let's do that.
Okay. So remember that inflation is this very fast, rapid expansion of the cosmos. And obviously the universe is not expanding at that incredibly fast rate now, or at least our observable patch is not. So obviously inflation is, and in fact it's modeled as something that is inherently unstable. So it has to end. And then we get to a sort of more leisurely rate of expansion. But the way this ends, it's a quantum mechanical process. So it decays. This inflating space decays a bit like a radioactive element decay. So it has a half-life. So half of it decays at any given time, and then the other half, that starts to decay and so on. So inflation does exactly the same thing. The inflating space decays, and then in our patch, it's gone. There's no more inflation. But there's a very novel twist about this. It's very different to a radioactive element. And it has a very surprising consequence. And it's this surprising consequence that leads you to a multiverse. So the analogy I like to give is that imagine my mother makes this incredible chocolate cake. It's so delicious. So she puts it down on the table, and immediately half the cake is gone, and we've all had a slice. And then, a couple of cups of tea later, we have our seconds, and now the cake has gone, right? So how many slices of cake have we had each? 2, let's say, okay? And that's it, and then the cake is gone, so you can't have your cake and eat it, right? So, however, let's imagine that the cake behaves like inflating space. So this cake, we have a slice, then when we go back for our second slice, in between, the cake has grown exponentially in size. And let's just imagine that the cake is always growing faster than we can cut it. How many slices of cake can we now have?
Well, it's
as
unlimited.
many as you want. Yeah, it's unlimited.
Right.
Awesome.
It's unlimited.
And the neighbours.
Right. Yeah, brilliant. So you can have your cake and eat it if it's made out of inflating cake material, right? Now it's the same here. When inflation ends, remember, we get a big bang. So that creates what we call a pocket universe. But there's always another bit of inflating space that's left over. And what is that doing? Well, it's growing exponentially. So as long as that exponential growth is faster than the rate of decay, then it will make not one pocket universe, but an infinite number of them. And in pretty much all models of inflation, this has to be the case, that inflation grows faster than it decays. So as long as you have that, then you'll get a multiverse. So it's called eternal inflation. So that means that our pocket universe is just one of an infinite number. And now then you could ask the question, well, was there a first one? And if there was a first one, what are the odds that we are in it? So obviously the odds that we are in it are infinitely small. But was there a first one? Well, there's a theorem called the Border-Guth-Vilenkin theorem that says there was a first one. So this eternal inflation, even though it's eternal into the future, cannot have been eternal into the past. And this is important because when inflation was first developed, people realized, as I said, that it violates the Penrose-Hawking singularity theorem. So maybe you could imagine that inflation implies that the universe is eternal into the past. But what Border-Guth-Vilenkin seem to be saying is, no, that's not the case, that inflation cannot be eternal into the past. But that does not mean that the universe cannot be eternal into the past, because there could be a contracting phase before inflation. And in fact, there have been models of inflation which violate this Border-Guth-Vilenkin theorem. So there have been models of what are called past eternal inflation, where people have found ways to get around this Border-Guth-Vilenkin theorem. And in fact, Alan Guth himself has suggested one. So people have projected this particular theorem as proving that the universe had a beginning, but it doesn't prove that at all. At best, it proves inflation had a beginning, but even there, there's some dispute. And of course, there's no chance of any observational evidence that would determine this, because, imagine this inflating space and infinite pocket universes, and eventually you go back and there's the first one. Are you ever going to see any trace of that first one? There's no way we can even conceive of that.
Right.
And would each of the multiverse universes have the same beginning conundrum that we've got here? To go back to the time reversal one before our
Okay,
Big
well,
Bang,
we have
would
to
each one be
distinguish.
in a pair like that?
No, they wouldn't be paired. The bubble universe would not be paired up that way. But you could imagine a process of inflation happening in both directions of time. So there would effectively be two seas of bubble universes, I think.
Right.
That's how I understand it. But you can watch our video and have Alan Guth explain it to you, and he certainly will explain it better than I can. But he doesn't actually mention whether it's sort of two seas of bubble universe, but that's how I would picture it. But but no, that each bubble is not paired up with each other.
Okay.
Yeah.
So if we're headed in one direction, the arrow of time is headed toward inflation on our side of this cosmic subway,
The
right?
arrow of time's not heading towards inflation. The inflation is in our past, not necessarily in our future. Although you could imagine that there could be some inflation in the future, but inflation is something that happened is generally in our past.
Okay, fair enough.
Yeah.
I guess
Although
my
there are
question,
models where effectively inflation happens in the future, but those are cyclic models. That's a different model.
sorry, so I'm guilty of using the wrong term here. So yeah, inflation is in our past. I should have used the word expansion. So my apologies, because our
Sure.
universe is
Yeah.
continuing to expand.
Right.
So I apologize because that's really sloppy. But expansion is in our future. And that's sort of the way our time is lining up, is that the universe is continuing to expand. And if we were on the other side, so right now galaxies are red shifted from us, right? They're getting further away and and faster. It seems like the people on the other side of this thing would have the opposite effect. Wouldn't they see that they were heading toward contraction because of blue shift?
So it depends on the model. There are certainly models which you would exactly see that. Yes.
Okay.
But it depends on the model.
I remember some of the early conversations about multiverses, and forgive me if I'm remembering badly here, but I remember some kind of imagery of multiverses were kind of like a sea of foam bubbles on top of water, where all the universes were pressing up against each other. And you might see the impression of another universe on the edges of our universe. Is that something that's still being taken seriously, or have we pushed that aside now?
Okay, so yeah, let's go into that. So basically, it's not right to say that the bubbles are pressing up against each other. They're not. There's an inflating space. So let's imagine we've got a pot of water, and in fact, the physics of this is similar. So when we boil water, bubbles appear, right?
Mm-hmm.
And the water turns into bubbles, and the bubbles sort of disconnect from the pot of water and so on. So now imagine that this pot of water is rapidly expanding, and in that expanding sea, bubbles form. Okay. Now it's possible that somewhere in our past, as it were, two universes formed close to each other and bumped into each other before they could be stretched away from each other. So it's possible, but it's not necessarily something that we should see. We just have to be lucky. If we're lucky, this happened, and we could see it. But I mean, if we're unlucky, there was too much inflation, it would erase any trace of this. So we have to get lucky and see this, and we could see it. So people have looked at the cosmic microwave background to see if there are traces of a bubble universe colliding with ours. So at first, when it was first looked at, there was nothing definitive. There were 4, I would say, candidates for a bubble collision, but they didn't have the statistical significance that was needed. So that was first done with the WMAP data. Now, WMAP was a satellite sent up by NASA to map the cosmic microwave background. Now, there was a follow-up spacecraft called Planck. And Planck looked at this as well. They didn't find the same thing. They didn't find anything definitive, but there are weird anomalies in the data, in the WMAP data. So there's this big cold spot, and people are perplexed by this. This kind of shouldn't be there. So could that be the sign of a bubble collision. It could be, maybe, but there's nothing definitive about this, and it's not clear that the cold spot is even a real feature. But what was interesting was that when Planck went up, which was a more high resolution spacecraft that the European Space Agency sent up, people thought that probably these anomalies would go away. That you've got a better resolution spacecraft. This is just noise in the data. It's going to go away, and then they didn't go away. Those anomalies were still there. So are they a sign of a bubble collision? Certainly, we can't say that, but maybe it could be. One thing that might happen in the future is people look at there'll be new missions to look at the polarization of the cosmic microwave background, and maybe that could help us decide on this. But at the moment, I would say search for bubble collisions has been disappointing. We haven't seen anything with any confidence, and you need a high level of confidence if you're going to claim something like that. However, if you want to look for experimental signs of a multiverse, if you wanted to make the case, as it were, that there's experimental evidence for a multiverse, probably the best bet for you would be to say, look, we've got evidence of inflation, and most observers would agree with that. Although, as I said, that is far from unanimous. There are definitely some well-respected cosmologists that would dispute that. But it is the consensus view. And then you could say, and inflation is likely eternal. And in fact, the type of inflation that the Planck satellite favors, there are different models of inflation. And the type of model that I believe is favored is quite easily, looks like eternal inflation. And in fact, in our film, we interviewed Georges Efstathiou. And who's Georges Efstathiou? He was the person that the European Space Agency chose to be the person that presented the cosmology results for the Planck spacecraft. And when we interviewed him, we said, what's the nature of the observational evidence in relation to the multiverse? And he said, well, Planck favors models of inflation that look like they generate a multiverse. So I said, do you mean to tell me that you've got evidence for a multiverse? And he said, yes. So, but that is still a controversial statement. I'm not sure everyone would agree with him. But nevertheless, the fact that the person chosen to give the cosmology results, he's an extremely well thought of cosmologist, one of the top observational cosmologists in the world, is making a statement like that, certainly means that this is something to take seriously, but not necessarily something that you have to agree with. I mean, the evidence is very debated, and it's not something, where it's not like, humans and chimps share a common ancestor. If you don't believe that, you're irrational, I think. The evidence is overwhelming. This isn't like that. This is something where the evidence is hotly debated. What does this mean? So a lot of back and forth about that, and certainly that's controversial.
Is there any anticipation that the James Webb Space Telescope will help with these observations?
No, as far as I know. James Webb Space Telescope is not designed for that. It is designed to look. There are future space telescope missions and ground-based telescope missions that may help us in this quest, but I don't believe that James Webb is in any way designed for that. It's designed to look at the earliest galaxies. Now, maybe you could make a case. One way to try and test some of these early universe models is to look at the distribution of galaxies, because it's thought that the distribution of galaxies was seeded by the very earliest moments of the expansion. So maybe some of these models, bouncing models and other models, can describe this distribution of galaxies. And James Webb will help us with that, because it's designed to look at the very earliest galaxies. That's really what it wants to do.
Largely a Hubble replacement, but better instrumentation.
It's got a much bigger mirror, but it's a bit different because Hubble is mostly in sort of optical and UV part of the spectrum, whereas James Webb is looking at infrared light. But what we want to look at for the early universe are two types of things. Actually probably more than two, but it's mostly cosmic microwave background. So what a space mission the temperature differences in the microwave background have been studied in a lot of detail, but the next thing to look at would be the polarization of that. So now people are trying to get a space mission to look at that, and that would certainly help a lot. And then the biggest thing is gravitational waves. So this is a brand new form of astronomy. The first gravitational wave is only, what was it, 4 or 5 years ago? 2016?
2016. 2016.
Yeah.
Yeah.
So it's very new, very, very new. And gravitational waves is really the best probe for this. And I'll tell you why. Because, but also what makes them the best probe is means they're the most difficult to detect. So these two things go together, unfortunately. So basically, the cosmic microwave background is light, yeah, and it makes, unfortunately, the universe you cannot see earlier than the cosmic microwave background, which was emitted roughly 400,000 years after the Big Bang expansion started. So you cannot see with light anything earlier than that, although you can make inferences about it by looking at the temperature differences. So you want to find something that, so if you like, this light is like a wall. It's like trying to see the center of the sun. You can't, right? Because the sun is not transparent. Yeah.
Mm-hmm.
So it's like a fog, and you just cannot see through this fog. So what you want is, but there are things that come out of the sun that you can see from the core. So they have to, but in order to see them, they have to interact very weakly with everything else. And if they interact very weakly with everything else, that means maybe you can see past this fog, right? They can go through the fog. But if that's true, it's hard to detect them, right? Because they don't interact with your detector either, right? So there are two things that we could see that are prior to this fog of the cosmic microwave background. So one is neutrinos. Neutrinos are these particles that are kind of, barely interact with anything. I mean, for a neutrino, most of the universe doesn't even exist because they just don't interact with it. They don't feel it. They don't see it. It's just, there's no interaction with any. And so neutrinos are very weakly interacting. And to see them at all is a very big challenge. So neutrinos can go through this fog. But even better than neutrinos are gravitational waves. But these are very, very hard to detect. And we've detected gravitational waves from black hole mergers, but not from the primordial universe. But in the future, there are missions to try and detect gravitational waves from the primordial universe. And that is really probing as early as we can go. And maybe you could effectively almost see the Big Bang happen with gravitational waves, or what was before the Big Bang. So there is, if you like, hope for experimental probes of these very primordial eras, but they are very difficult because they have, by definition, they have to interact very, very weakly. The other thing, though, is just better analysis of the cosmic microwave background, and by looking at the polarization and other features, then we can try and hone things down and rule out some models, and other models can be more favored. And I think it's a question of, the way I see science is, it's like a competition, and the idea is to eliminate the competitors, and hopefully only one is left. And so that's what what cosmologists are trying to do.
Science is evolution. I love it. It's may the strongest theory survive.
Yeah. Exactly. Well, absolutely. The fittest survive. And that's the game at the moment. The idea is for theorists, if you like, to dream up models, and then for people to try and find ways to find, well, what are the observational signatures of those models, and then go and look. And I think a lot of exciting new projects, ground-based telescopes, space-based telescopes, neutrinos and gravitational waves, that will help us try and narrow things down. But of course, work has to be done on the theory side, because these theories make sort of rough predictions, but then they're trying to get them more precise, and less ambiguous, because there are difficulties. You have to make assumptions about, well, what was the matter content of the early universe, and then what is the model that I'm going to try and use. So for example, you mentioned loop quantum cosmology. So they've got this bounce, so they're very clearly telling us there was a bounce. But in order for that to turn into a prediction, they have to make some assumptions about, well, was there inflation or not? And if there was inflation, were there different types of inflation? So what type of inflation? So what they can do is say, well, look, if I assume this type of inflation, then I can make these predictions for the cosmic microwave background. But, of course, you could always say, well, it's not really a prediction from the model. It's the model plus an assumption of what's the matter content of the early universe. Was it an inflaton field, which is the field that's supposed to generate inflation, or not? And there are other things that can help us tell us whether inflation happened, or maybe one of the alternatives to inflation. We haven't really mentioned those, but one idea is that maybe there wasn't this great big exponential expansion. Maybe the speed of light was much faster in the past, or maybe there was a cyclic universe that in the pre-Big Bang universe it sort of mimicked inflation. So all these ideas are being explored, and there's exploration on the theory side, trying to make more precise predictions, and on the experimental side, trying to get more information about what the early universe looked like. But at the moment, the situation is we know there was some type of Big Bang event. There was a hot, dense universe. And then what happened before that? Well, most cosmologists think there was inflation. And if there was inflation, it looks like there's a multiverse. But of course, you could always challenge that. Maybe we've misunderstood inflation. Maybe inflation happened but didn't generate a multiverse. That's always a possibility. And then if inflation did happen, well, what happened before inflation? That is in the realm of quantum gravity. And people are working on theories like string theory and loop quantum gravity and Hodge and Lifshitz gravity to try and answer those questions.
So I don't know if we have time for this, and Matthew, you tell me whether we should do this or not. But we've talked a lot about models and theories, ways to sort of verify our models, to understand what models might succeed and what models might not. As a science writer, if we want to go this way, are there some practical lessons that you take away from this that you would like people to know about cosmology? Things that we hang our hats on that we shouldn't, and things that we should hang our hat on that we don't. Does cosmology have any practical? I almost hate to say this. Does it have practical philosophical implications? And so putting practical and philosophical together might be.
Okay. So all right. So let's first off. I think there are a couple of misconceptions that I think are abound in cosmology, the public's understanding of it. Biggest misconception is that we know that the universe had a beginning. So I think, as we've explored in this conversation, we don't know that. That's just wrong, as far as I'm concerned. It's not wrong that there was a beginning. There might have been a beginning, and we haven't talked about models that have a definite beginning. Alex Vilenkin, I think, has a very interesting model that I think clearly has a beginning to it, and that might be right, but we certainly don't know it to be right. And again, we made a film with him about his model. We call that A Multiverse from Nothing. So look out for that film in our series. And so it's certainly conceivable that there was a beginning, but we don't know that there was a beginning. And so that's a misconception we should clear up. Other misconception that we should clear up: inflation happened after the Big Bang. Again, given that we've redefined the Big Bang, it's probably better to say that if inflation did happen, and that's an if, then it happened before the Big Bang. And then maybe another misconception is that the universe is not going to recontract. It's going to expand forever and we're in for a heat death. Well, that is true if dark energy is a cosmological constant. And it might be. And it certainly, that is consistent with the data. But I don't think we have the confidence enough to say that is definitely going to happen. That is probably going too far. So those are some misconceptions. So about philosophical implication, of course, people want to know, I think the purpose of, there's two, if you like, purposes of cosmology. One is it's just a laboratory to study physics at very high energies, because we cannot build a particle collider that can probe the energies of the Big Bang, not even close. I've seen people say about the LHC that it's the Big Bang machine, that it probes energies just after the Big Bang, but not really. Right. I think that's misleading. I mean, in some sense, it's misleading. Of course, it is just after the Big Bang, depending on what you mean by just after. Because the energy scale drops very rapidly as the universe expands. So they can kind of get away with that. But what you have to know is that the energy scale that they're looking at in particle colliders is a teeny tiny fraction of the energy scale of the early universe. I mean, it's minuscule. So that you cannot build a particle collider to probe these energies. So cosmology is practical in the sense of it's a probe of physics at much higher energies. Of course, it's not going to lead to, some gizmo that you're going to have in your house. I don't think that's the case. So it's not practical in that sense. But in terms of what you meant was it going to inform us about philosophical questions?
Mm-hmm.
Well,
exactly.
Okay, so there are philosophical questions that have been raised in the context of cosmology. So I think there are two philosophical questions that sort of permeate the field in particular. One is, what is our ultimate origin? Does the universe have a beginning, or has it always existed? And we can sort of conceivably try and answer that. And people believe that it was answered, right? But now we found out that no, it wasn't answered. But that doesn't mean it won't be answered in the future. Maybe someone will be able to come up with a model that is clearly eternal in the past, or clearly the opposite. Has a definite beginning, and then we can test that. The other philosophical question that is often brought up is this question of fine-tuning of the constants of nature. So why do the constants have the values that they do? They seem to be, or it's alleged that they are fine-tuned for life. That if they were any tiny bit different, then life wouldn't emerge. And so you have to then ask, well, how did they get this unlikely value? And of course, some people will say, well, God tuned them because he wants life. Other people say, no, there's a multiverse. And of course, if you want to try and understand how it was that someone could win the lottery, well, one explanation is that you had someone rig the lottery for you. So that's, if you like, the God explanation. Another explanation is, well, there were a lot of lottery tickets sold. And if there was a lot of lottery tickets sold, you don't need anyone to rig the lottery. Someone's going to win it. And that's, if you like, the multiverse explanation. But there are so those are like the two most popular explanations for that. But there are others, and I think it's worth just mentioning the other ones. So another explanation is that maybe there's some Darwinian process of reproduction of the cosmos. So Lee Smolin has a model called cosmological natural selection, where the universe undergoes an evolutionary process. And if you shuffle genes randomly, the chances of you getting a genome that can make a complex organism are basically next to zero. So how is it that we've got all the right, sequence of DNA to give us this amazingly fit bodies, right? I don't mean I've got a six-pack or anything, but I mean
fit for our environment.
Fit for our environment.
Fit in this, right?
Right. Yeah. So and the answer is evolution, right? So Smolin has suggested there's some evolutionary process. And we made a film about that called Black Hole Genesis. So the idea is that black holes reproduce and create new universes, and there's a sort of reproduction. So that's a third explanation for this fine-tuning. A fourth one is, well, maybe the constants cannot change, right? So that they're just there by necessity. That you can't say that a 6 and a dice is unlikely if every single side of the dice has a 6 on it, right?
Right.
So that would be, the answer would be necessity, that the constants have to take on those values. There's some mathematical reason why the constants of nature have the values that they do. And then another explanation, if you like, is that we're just wrong that the constants are fine-tuned. Maybe we're not justified in saying that. Maybe they could change and they could generate life and complexity, or it's really complexity rather than life. I think is at stake here. But maybe we're just wrong about that. And some people have suggested that as well. So I'd say so let's sum up. There's the God explanation, there's the multiverse explanation, there's the evolutionary explanation, there's the necessity explanation, and there is no fine-tuning explanation. So there's sort of 5 possibilities there. And there's been attempts to try and tackle this with experiment. Could we experiment whether there is a multiverse or not? Could we make a prediction about what would happen if there was a multiverse? And there are claims that Steven Weinberg, who's a Nobel Prize-winning physicist, made a prediction based off this sort of multiverse reasoning as applied to fine-tuning, and that he predicted that the cosmological constant has the value that it does have. And he was actually right about that. He did make a successful prediction, but there's a lot of controversy about how to interpret that. And so I certainly would want to say, therefore the multiverse is proven explanation of fine tuning. Certainly that's not where we're at, but it certainly, is a feather in the hat, as it were. But as I say, there's a lot of controversy about how to interpret that. So those are what I would say are the philosophical sort of big topics around cosmology. But another sort of issue is, what is the nature of science? Because, cosmology is an interesting one because we don't get to look at multiple universes. I mean, there might be multiple universes, but even if there are, we're not going to get to see them. Right. And so what is the nature of science when you can only look at one outcome of an experiment? You really would like, in any experiment, what you'd like to do is run them loads of times and then get data on them. But, in cosmology, you can't do that. So there's a lot of discussion about what is the nature of science. And there's a multiverse and then maybe anything can happen. Is that science? Because if anything can happen, well, what does it mean to make a prediction? So there's a lot of complexity around those issues. So those are sort of, if you were to ask, what things are discussed in the philosophy of cosmology, I'd say those are sort of some of the topics that would be that cosmology addresses.
So thank you for that, because I think that what I see at the sort of popular level, right? I like this stuff, but I'm not an expert. And I have to say that this conversation helped disambiguate a lot of the ideas that I had about cosmology that I'd sort of gleaned from various models and sort of cobbled together in some strange way, right? And so this was very helpful in terms of disambiguating those ideas. And I think it is useful to take that and sort of apply it to what we think cosmology is teaching us, and maybe to be a lot more philosophically humble about the conclusions that we draw from cosmology, because right now it doesn't seem like there are a lot of stamps of approval that we can just go to the wall with.
Well, let me say that we have learned a lot about the universe.
Sure.
I guess we're focusing on the questions that are interesting, and by definition, they're the open ones, right? Mm-hmm. There are things that we know with very high levels of confidence. The universe is expanding. There was some sort of Big Bang event. There's galaxies and large clusters of galaxies, and they have a certain distribution. And there's a lot of things that have been learned in the study of cosmology. But yet there are, of course, a lot of things that are still open questions. And also cosmology poses questions that we didn't know were even questions to ask. So we've learned through cosmology that the things that we're made of, atoms, only make up a tiny proportion of the universe. So, we think that roughly speaking, it's something like 5% of the universe is made out of atoms. About 20 something percent is made out of
26 or 27.
Yeah, okay, something like that. So 20 something percent is made of dark matter, and the rest is dark energy. We would not have known that without cosmology. We only know that because of cosmology. So we've learned a lot through cosmology, but there's a lot more to be learned. And there are
absolutely
that we thought we knew that we've now realized that we don't know.
As a teaser, because you brought up dark matter, do you have a video on your channel or a series of videos about dark matter? Because I know we don't have time to pull that apart.
No,
and it wasn't really.
I haven't covered that, but it would be an interest. If I had an infinite amount of time, I probably would. Models of dark matter, and some people that propose that there is no dark matter, that instead we have to modify our rules of gravity, and that is, I think, a reasonable competitor to dark matter. But all of the different models have their pluses and their minuses.
Sure.
So dark matter can explain things very, very well. The only problem is we just keep failing to see it. And when I say see it, there are detectors that should detect it, and they just haven't.
Right. Weakly interacting massive particles, etc.
Yeah. So on the flip side, modified gravity models have their problems trying to account for the cosmic microwave background. So there are difficulties on both sides, I think. And I think you could make an interesting series about that, but I just haven't got time. But that is a pretty fascinating topic. But I would say that it doesn't really reflect on the bigger question. To me, I think if I ask myself, if I could just know the answers to scientific questions, which questions would I like answered? And I think the two that I would probably like to answer the most is, where do we come from? What's the ultimate origin of the universe, or does it have an ultimate origin? And I guess the other one would be, are we alone in the universe? Is there aliens out there? As opposed to, what is the nature of dark matter? Well, that is a very fascinating question, but personally, it's not one that fascinates me enough to want to spend years of my life working, interviewing all the people about it, because making these films is actually a big effort. I have to do a lot of homework.
I'm sure it is.
To get the right people and ask them the right questions, and then go away and film them, and then edit it all together. So it's a lot of work. And doing a series about dark matter, maybe I might do that in the future, but personally, it doesn't. I don't find it quite as fascinating as, what's the origin of the universe.
Right. I echo both of those questions.
Yeah.
Did the universe have a beginning? Which is really the sort of egocentric question. What was our beginning, right? And are we alone?
I think I think humankind has always wondered about origins.
Sure.
And that I think is a universal thing in human nature. We want to know, keep pushing the envelope of our knowledge. What happened before that? What happened before that? Where did we come from? And I think that's deep rooted in humanity. And that's why we should invest money in cosmology, because we're answering, or we're not necessarily answering, we may or may not find answers. We have to explore, we're exploring those questions. And I think the question of, well, what is the universe made of, is still an absolutely fascinating question. I don't find that, for me personally, and other people may differ about this, it doesn't quite tug at the heartstrings in the same way as, where do we come from?
Right. Right. And equal to that for me is, are we alone? Right.
Yeah. That's another big question.
Yeah, because if we never found out where we came, what our origin was, but we knew we weren't alone, there would at least be some satisfaction, right? We'd be able to maybe we'd be able to get along together. I mean, who knows?
I don't know. I don't. It would. But I do think there was a statement. I can't remember who made it. Maybe it was Carl Sagan. It was like, either we are alone in the universe, or we're not. And finding out either of those is incredibly profound.
Yeah.
But I have to say, we haven't covered that in our videos. That's another topic. But I find that fascinating.
Very fascinating. Thank you so much, Philip. It's been a genuinely really, really fascinating and really, really interesting last hour and a half. There's been some really good nuggets that I've picked up from there. Some new stuff for me, like the time going backwards. I'm gonna be dreaming about that, I think, for weeks. Right. I really, really am loving that idea.
But it's not like Tenet.
No.
And I want to ask, Tenet, someone tell me, what is the point of a backwards in time bullet? What does it do?
Yes, I know. My daughter. I know. My daughter wants to go back and watch it again. So
maybe it would become clear then. But I just figured, well, you would just unkill your target. Right? I just was like scratching my head, going, "What is the point of that?"
Yes.
But it was still a lot.
It was really good fun. It was a really good fun film to watch. Maybe we need to watch the film backwards. Maybe that's the answer.
I'm watching Dark, which is a Netflix time travel series, and I'm enjoying that very much.
Okay.
That's really, really good. But whether it will deliver at the end, I'm still watching it, so we'll see.
Oh yeah, it's all too often, isn't it, that things fail to deliver right.
It's going to be like moment. Lost, and there's going to be no there.
Well, I hope not. We shall see.
Excellent. Well, thanks again, Phil. Sorry,
thank
Andrew.
Thank you very much for having me.
Oh, I was just going to say you're off on vacation. I was going to wish you a happy holiday as you're
I'm
as
not
you're
on
off.
vacation. There's no.
It's
Yeah,
not really.
Matthew.
No, it's
Go
just a
ahead.
weekend away. It's
Oh,
now
Where
my
are you
it's
going?
1 o'clock in the morning, and it's now my birthday. So I'm going
Happy
away
birthday.
for a nice weekend
Where
in
are you going?
Bristol,
Okay.
just to
Have a
Bristol.
nothing
I'd
So.
more.
say happy birthday, but I know how old you are. No, happy birthday.
Thank you.
All right. Have a
And
good one. Enjoy. Hope you have a nice
Yeah.
Phil,
break as
Yes.
well.
thank you for joining us, man.
And
It
Okay.
was fantastic. Thank
All
you.
right.
there'll be
Thank you very
links to all the YouTube videos that you flagged up in the episode in the show notes for the benefit of listeners, but I recommend that they go to your channel anyway and start digging around. But the specific videos that you mentioned during this conversation will be in the show notes.
Cool.
That's right. And if you have questions or you'd like to feed back to us, if you have comments on the show, or if you just want to say hello, reach out to us at reasonpress@gmail.com.
You have been listening to a podcast by Reason Press. To get in touch, email reasonpress@gmail.com or see our website reasonpress.net, where you'll also find our book Still Unbelievable. We welcome all feedback, and you might even end up on an episode. Our theme music was written for us by Holly. You can hear more of her music at soundcloud.com/hollybishop. You can support us by buying some of Holly's music and telling her we sent you.